just one quick slide. In filter terminology, we have this effective size, which we often abbreviate as ES. It's a sieve size that 10% by mass of the sand passes through. So it's kind of a smaller dimension, smaller size measurement of the sand. And then there's a D60. Why they didn't call effective, why they didn't call effective size, just always just call that one D10. And then D60 is the size, the sieve size that retains 60% by mass of the sand. And that's the size that we will tend to use, like if we're calculating head loss through a filter bed, a clean filter bed, we would use the D60 size in those equations. And then there's a uniformity coefficient, which is you divide those two. And what you would like is for, this is, you're dividing the sieve sizes. And what you would like is for those two sieve sizes to be close to the same, meaning that you have sand grains that are pretty uniform in size. So a uniformity coefficient of 1 would mean that the same sieve that holds 60% of it also holds 10% of it, which isn't quite possible, but it's like they're really, really close to the same size. So and see, this connects back with porosity, right? If you have a very uniform sand size in your filter, it's going to have a higher porosity, which is what you want, because in the filter, it's the pores that do the work for you, right? The pores are where you can tuck particles and have them removed, and it's the pores where the water flows through. So you want high porosity. So that means you would like a low uniformity coefficient, so it's close to 1. Here's a head loss equation, and actually there's two head loss equations that are commonly used. This is the Kármán-Kozény. It's the simpler of the two equations. I'm going to have you play with the ergon equation for the design challenge that I have coming up for you. The ergon equation is also in the textbook, and I didn't bother putting it here. You'll recognize all the terms in the equation. They're similar kinds of terms. The phi there, the phi filter sand is the porosity, and HL is a head loss, etc. What I want to point out, maybe of kind of interest from a theoretical basis, is remember a long time ago, we talked about the Hagen-Poiseuille equation. Hagen-Poiseuille is the equation that describes head loss through a long straight pipe under conditions of laminar flow. And I have it there in the upper right. And just compare the Kármán-Kozény equation and the Hagen-Poiseuille equation, and you'll see that a lot of the terms show up like exactly or almost the same. So the head loss term is the same, the length of the flow path, L, or the height of the sand column that it's flowing through, that's the same. There's some funky coefficients out front that are different, but don't worry about those. What we're interested in are the big parameters that have units on them. The porosity, of course, we don't deal with that when we're talking about the pipe, but kinematic viscosity shows up exactly the same. The velocity shows up the same in both equations to the first power. There is this definition of approach velocity that's used in filters, and I think I mentioned this. The approach velocity is the velocity that the water would have if there weren't any sand there. Or if you have a downflow filter, it's the velocity of the water above the sand as it's going down before it enters into the sand. And I think we did this last week where we looked at if once the water enters the sand, now you know the water speeds up, right? Once the water enters the sand, it speeds up because it has a smaller cross-sectional area that it's flowing through, the pores. And so it has to speed up to maintain conservation of mass. So in this equation for Kármán-Kozény, that velocity is not the velocity inside the pore, it's the velocity if the sand weren't there. And okay, D shows up exactly the same way and G shows up. So happily, both equations are dimensionally consistent and very, very similar. Okay. Now some fun with math. I don't know. Let's see. Fluids. How about statics? We're going to use statics to explain what the water pressure needs to be at the bottom of a filter in order to force that filter to begin to fluidize. Because fluidization is about a force balance. It's about there being enough pressure on the bottom of the filter to hold up all the water and all the sand that's on top of it. And if once that pressure meets that value, it will fluidize the sand. So we'll begin with, I should have put a point down here. Think about a point that is at on the very bottom of this apparatus, the very, very bottom, this dark line. Think of a point down there. And we're going to figure out what the pressure is at that point, first by working our way from the atmosphere down to that point through the sand bed. And then second, by going down through this manometer. And maybe what's not clear here is somewhere there's some water entering underneath this filter that is pushing water up through the filter. So water is flowing, but we can still use this statics argument to figure out what the pressure must be at the bottom of the filter. So let's add up the weight of everything that's inside the filter box. So that's what this first equation is. So we're going to take the density of water and G, gravity, and we're going to multiply it by the height of water 1. So HW1 is the height of water that was above the original sand bed. And also HW2, which is the depth of water that was below the sand bed. That sand is just magically held up by something, some sort of underdrain system that doesn't let the sand leak down through, or an infinitely thin layer of gravel. That might break your brain thinking about an infinitely thin layer of gravel. So an underdrain system that doesn't let the sand down through. So those first two terms are the weight per unit area of the water that's above the sand and below the sand. We have to also add the water that's in the sand bed, and we know that the amount of water that's in the sand bed is the height of the sand bed times the porosity. So phi times the height of the sand bed is going to give us the equivalent height of water that is filling up that sand bed. And then we have to add the weight of the sand itself. So now we take the density of the sand times G, and the equivalent height of sand with no pores is 1 minus the porosity. So 0.6 times the height of the sand gives us the height of the sand, if you could just like consolidate it into one solid chunk of silica. And so that gives us the pressure at the bottom of the sand column. And then we have to do the same analysis going up through the water column. And when we do that, we get this second equation, rho manometer is equal to rho water times G. And then we have to add up all the heights in the manometer column. We have H1 and HW1 and HW2, just like we did before. We also have the height of sand. There's no water in there. I mean, sorry, there's no sand in there now. That's just water. And then we have this new unknown term, which is the actual head loss that is happening as the water is flowing through this sand column. And that's a height that we're going to end up solving for. So those two equations for the pressure at the bottom of the sand bed, they must both be true we can set them equal to each other, and we can solve for our unknown, the head loss through the sand bed when we're backwashing it and it's fluidized. And we get this lovely, simple equation that says that it's proportional to the height of the filter sand, which makes sense. And then there's these two terms, 1 minus the porosity of the sand and the density of the sand divided by the density of water minus 1. And then this crazy thing happens. And I want to make sure that you catch this, that this crazy thing that happens is not something that is a universal truth. It's true with a particular kind of sand that has a particular porosity. And that is, if you have silica sand with a density of 2650 kilograms per meter cubed and a porosity of 0.4, when you plug those two numbers into the second two terms in that equation, 1 minus the porosity and times the density of sand over density of water minus 1, you get 0.99, which is pretty darn close to 1. Whew, take a deep breath. This means that when you fluidize a sand bed, the head loss through the sand bed is equal to the height of the sand before you fluidized it. Or watch this little animation. Or that is true, that the height of the original sand before you began to fluidize it is equal to the difference in the water level between what's in the manometer measuring the pressure at the bottom of the filter and the water at the top of the filter. I'm curious, does somebody want to ask a question? Because these are just crazy results. Don't be shy. Say, Monroe, this makes no sense at all. Okay, well, let's change this. Supposing we use garnet, and garnet has a density, I forget what, I think it's closer to 4,000 kilograms per meter cubed. What would you get in the case of garnet that is so much more dense? What would you find out about the head loss through that bed required to fluidize it? Do I still multiply by 1? As in, if it's garnet, we can say the porosity is still the same, but the difference is that the density of sand, density of garnet, is a whole lot greater. So that rho sand over rho water minus 1 is going to be a much bigger number. And that means that the head loss is going to be a much bigger number too. So if you're trying to fluidize garnet, it's going to require a whole lot more head. And so, like, here's one very simple practical result. Our stacked rapid sand filters are very carefully designed, and they're designed for using silica sand. And if you, as a very clever engineer, said, I think it'd be more fun to use garnet in those crazy stacked rapid sand filters, and you replace the sand and took out the silica sand and put garnet in it, and then you tried to backwash it, it would be a complete fail. The filter hydraulics aren't capable of delivering enough pressure to backwash garnet. Anybody want to ask a question?